Hello, everyone. I'm Jan, and I have a dream that together our community can build out a new ecosystem of reusable, custom extensions-based accelerators that work well together and that can plug into any FPGA RISC-V system. In this talk, I'll explain what this is all about and how you can get involved. It's now the winter of Moore's Law. Transistor scaling continues, but with quite modest improvements at each new technology node. So to keep advancing, there is tremendous pressure to add ever more domain-specific accelerators into every market segment. Whether your phone or car or base station or data center, your rich, complex software stack will need to use not one, but many accelerators. How are we going to deal with this? And how are we going to enable this? We can categorize all these accelerators according to how software manages and interacts with them. Most fall into three categories. The first is accelerators that provide a set of custom instructions, called a custom extension. They tend to be low latency, synchronous, and trivially synchronized to the instruction stream. While some may access shared memory, all benefit from super-fast direct access to CPU state, such as the integer or vector registers. Streaming data flow accelerators are another type, in which software explicitly sends and receives streams of messages composed with other streaming accelerators over a data flow graph of channels. And the third are standalone accelerators, programmed using work submission queue and completion queues in shared memory. Here, software has an async model, submitting work of unknown duration and separately processing completions as they come in. While all of these accelerator types merit their own standard programming models and hardware-software stacks, our focus today is upon custom extensions-based accelerators. This is so important that we have started a new task group within RISC-V International, the Composable Custom Extensions Task Group, to make it easier to create and reuse custom extensions-based accelerators. Reuse of multiple custom extensions is rare, in part because different custom extensions can conflict in their use of custom instructions and custom CSRs, and because there's no common programming model or API for custom extensions. It's unfortunate that it's so hard to build upon each other's good work. So the Soft CPU SIG have spun out a new Composable Custom Extensions task group. This group will specify new ISA extensions and non-ISA interop specifications for the decentralized and cooperative reuse of the custom instruction and CSR space, remaining compatible with existing custom extensions and uses. This enables routine reuse together in one system of multiple independently authored composable custom extensions, their software libraries, and their modular hardware implementations. To be clear, the group will enable an entirely opt-in, managed subcategory of custom extensions called Composable Custom Extensions that are backwards compatible with uses of other custom extensions. This task group will make it practical and routine for anyone to create, reuse, and combine custom extensions, their libraries, and hardware. The key prize is enabling a plug-and-play mix-and-match ecosystem of reusable custom extensions IP, providing system designers a ready catalog of accelerator solutions that work together, and providing accelerator designers a much greater addressable market. This is great for FPGA Soft RISC-V Systems, where you'll be able to compose reusable accelerators and libraries into new accelerated SoCs in an hour. Here's the backstory of this work. In 2019, the new Soft CPU SIG set out to specify a common logic interface for custom extensions-based accelerator cores, then called custom function units, or CFUs. And they sought to improve reusability by supporting composition of custom extensions and extension libraries. They wrote a spec, the draft proposed Composable Custom Extension spec. It's about 50 pages, 1/3 introduction, 1/3 ISA extension spec, and 1/3 logic interface spec. Variations on this logic interface have been used in the VEX RISC-V core, the CFU Playground for tiny ML accelerators, and FPGA soft and hard RISC-V cores from Lattice and Efinix. AMD Xilinx has a prototype implementation. This spec now serves as a non-binding basis spec reference design for the task group. This year, the task group was formed and approved, and it's now active and in the planned milestone. The task group will specify as a framework the minimum set of ISA and non-ISA standards up and down the stack that are needed for the practical reuse of composable extensions, libraries, and hardware. This includes specifying criteria for a custom extension to be deemed composable, and ISA extensions for conflict-free reuse of custom opcodes via CX multiplexing, for uniform extension state context management, and uniform privileged access control to extensions, and a common programming model with uniform means of naming, discovery, state management, etc., and an ABI for correct composition of custom extension libraries. And finally, an optional logic interface standard for reusable hardware implementations of extensions that automatically compose together and plug into extensible processors. That's the main theme of this talk. A proof of concept will require significant software and hardware development in SPIKE and QEMU emulators, soft processors, firmware, Linux, a CX API runtime, and example composable extensions and libraries. In the next few slides, we'll see how composition of independently authored custom extensions, libraries, and hardware might work in detail by discussing how it was done in the older basis spec. Keep in mind the new task group will take its own fresh look at this mechanism. Here are some examples that illustrate how various systems and software might be composed of separately authored reusable components. As usual, an application is built up from various separately authored software libraries. Here, these specific CX libraries can use various composable extensions custom instructions if implemented in the system hardware. So to build a system with the extensions these libraries require, we'll start with a catalog of reusable composable extension units, CXUs. A system manifest configures the system with a specific set of CXUs, and then some kind of composer tool generates a processor complex, including the specified CXUs and interconnect. The tool also produces a system CXU map, possibly part of the device tree, indicating which composable extensions are implemented by CXUs in this system. Then, at runtime, each of the application's MPEG, MXFP6, and P4 libraries use the CX API to discover whether their extension is available and then select it prior to issuing its custom instructions. By first selecting the Heart's current extension, each extension can use all of the custom opcode and CSR space conflict-free. Here the design has been re-implemented in vendor B's FPGA with a B RISC-V core, a simpler interconnect, and 2 of the original 3 CXUs. The exact same application runs on this hardware, although here the MXFP6 library discovers that its extension is not available and must fall back to pure software. Here's a sketch of a simple C binding of a programming model for CX libraries, one that might not require compiler code gen changes. Here, a myCX library calls the CXOpen API to dynamically discover if the extension is available. In the basis spec, a 128-bit UUID is the canonical name of this specific immutable version of the myCX extension contract. If the system implements the myCX extension, and the API will then return an opaque CX selector, here called cell. Then, for every client API call into the library, if the extension is not available, the library performs a pure software implementation of the computation. Otherwise, the extension is selected. The CX select function inlined, writes a selector CSR and selects the stateful myCX extension. Then the library issues a series of inlined myCX custom instructions that go to the myCX extension. And then a CX deselect restores the system's built-in custom instruction behavior if required by the CX ABI. So at the heart of the CX framework is a new ISA extension to multiplex the custom opcode space, enabling unlimited, conflict-free reuse of custom opcodes and CSRs. Here's how it works in the basis spec. On power on reset, and whenever multiplexing is turned off, the system's pre-existing built-in custom instructions operate as before, unchanged. Later, an extension library is called. It must discover if its extension is available and then select it prior to issuing its custom instructions. Discovery is performed in software in a CX runtime or CX-aware operating system, mapping the extension's universally unique CX ID into a system and heart-specific CX selector value. Writing this value into the selector CSR enables extension multiplexing and selects the heart's current composable extension and the extension's current state context. Then, in response to issuing a custom instruction, the CPU partially decodes the instruction, fetches register operands, and sends an extension request with the current state ID, function ID, instruction, and operands off to the selected extension. The extension will perform the function and/or redecode the whole raw instruction to address extension-scoped registers. It possibly updates its state, and then a few cycles later, the CPU uses the extension response to update a destination register and the CX status CSR. This diagram illustrates this process. Running the code on the left, we've just moved the value of x10 into the CX selector, and now we're executing the CX reg custom instruction that follows. This creates a CX request comprising the CXU-ID and state ID from the CX selector, the raw instruction and function code of the instruction, and two source data operands from the register file. This request selects a specific CXU and a specific state context within that CXU, and provides the operands to perform the selected custom function, possibly updating the state. The response data is written back to the destination register, and any error response status is accumulated in the CX status register. So now let's look further down the stack into the design considerations for a common logic interface for CX unit hardware, again drawing specific details from Chapter 3 of the older basis specification. First, let's review some CXU-LI design objectives, which are all pursuant to our overarching goal of practical, dependable, and routine reuse. An ecosystem of composable extensions requires modular and portable composable extension unit hardware cores, or CXUs. We must be able to automate composition of complexes of CPUs and CXUs, and do so without having to change or revalidate any CPU or CXU RTL. We must handle diverse CPU microarchitectures, from simple MCUs up to complex out-of-order multi-issue processors, and diverse extensions with simple ALU-like implementations or with complex and deeply pipelined data paths. The interface logic and signaling must be gate and LUT frugal, so it's affordable in tiny systems and affordable in many core systems. And the logic interface must promote uniformity, uniform port signals, naming, and parameters, and someday, but not a task group deliverable, common interface validation tests and metadata. So here are CXUs in a nutshell. A CXU implements one or more composable extensions custom instructions. As the CPU issues custom instructions, each becomes a CXU request routed to the selected CXU, which performs the requests in order and sends CXU responses back to the CPU updating destination registers and CX status. CXUs are highly configurable with parameters like port widths, latency, and state context counts, and with valid parameter values that we expect will eventually be described in CXU metadata. The CXU logic interface supports different CXU feature levels, reflecting different levels of sophistication of CXUs. It efficiently supports combinational CXUs, pipelined fixed latency CXUs, variable latency, valid ready handshake streaming CXUs, and even response reordering CXUs. A given CXU or CPU speaks a specific CXU-LI feature level, and then systems are composed from these using parameterized switch and adapter CXUs. The 4 feature levels in the basis spec are stratified to factor out boilerplate complexity and overhead, to keep simple cases simple and frugal, while still supporting complex use cases. So it works well for simple and complex CPUs and for simple and complex CXUs. For example, some CPUs can tolerate fixed latency CXUs, but cannot tolerate flow-controlled back pressure from a CXU. So level 0 is a combinational CXU with ports signaling the requested CXU and function and data operands, and with response data and status. Level 1 is for fixed latency clocked CXUs, which add a clock, reset, clock enable, a state ID, and a response valid signal. Level 2 is for variable latency streaming CXUs, adding valid ready handshakes on requests and responses, and level 3 is response reordering CXUs. The basis spec also defines feature level converter CXUs that adapt request and response channels up to higher feature levels so that you can use a level M CXU in a level N system. The CXU-LI enables automatic composition of CPU and CXU complexes. Composition configures the CPU and CXU RTL modules with compatible parameter values, and then inserts switch and adapter CXUs to wire everything together. Since both CPUs and CXUs may issue requests upon other CXUs, the components can form a directed acyclic graph. In this example, there are 2 CPU cores. Each can issue requests to any of 5 CXUs. But here CXU3 is feature level 1, while the rest of the components are feature level 2. Therefore, the first step of composition is to insert an adapter to raise CXU3 from feature level 1 up to feature level 2. And now all that remains is to insert some switch CXUs. The first routes requests from the CPUs to all the CXUs, and the second routes requests from the CPUs or CXU2 into CXU1. So, composition of CXUs is a configuration constraint satisfaction problem, finding a common feature level, port widths, latencies, etc. Recalling the custom extension multiplexing figure we discussed earlier, let's consider how that translates into the signals of CXU-LI. Reviewing the request and response ports in the table on the right, request ID is just a sequence number provided by the CPU. Request CXU and state are subfields of the MCX selector CSR. Request instruction and func come from the instruction. Request data 0 and data 1 from the integer register file or an immediate value. Response ID is just the request ID. Response status is merged back into the CX status CSR, and response data is written back into a destination register. This single table summarizes all the CXU-LI request and response port signaling across all feature levels. Some ports have a configurable width parameter. For example, you can configure the CXU data to be 32 or 64 bits wide. Some ports are optional and may be deleted with a width parameter of 0 bits. The key takeaway here is this is a simple and austere logic interface, scalable and accessible to many different kinds of CPUs and CXUs, and yet it supports important CX framework requirements, including dependable composition of extensions, efficient extension versioning, and multiple state contexts. Now we'll briefly consider some of the CFU feature levels with simple waveform examples. The first is CXU level 0, combinational CXUs, that supports only stateless extensions because there's no clock. It computes a combinational function of the request function and data, and it sends a response status and data after some delay. Feature level 1 supports fixed latency clocked pipelined CXUs. The CXU computes a function of each request and some private state, if any, possibly updating the state, and sends a response after the parameter CXU latency number of cycles. Some CXUs support a CXU latency down to 0 cycles, so they can respond in the same cycle as the request. The initiation interval is 1 per cycle, so the CXU can process a request every cycle, and there's no flow control. Clocked CXUs do have optional clock gating to enable power, so by negating the clock enable input, it will suspend the CXU interface and internals. And this works well on FPGAs whose flip-flops all have a free clock enable input. So in the waveform on the right, the CXU has a latency of 2 cycles. The first 2 requests arrive in cycles 1 and 2 with responses in cycles 3 and 4. The next 2 requests come in cycles 5 and 6, but then the clock enable is negated, freezing the interface through cycle 20. The final 2 responses come in cycles 21 and 22. Level 2 is for variable latency, or streaming CXUs, which compute a function of each request and its state, if any, updating the state, and then sending a response in order in a later cycle. Both the request and the response have valid ready handshaking flow control, so the CXU can suspend incoming requests, and the CPU can suspend incoming responses. Of course, this significantly complexifies the design of the CPU and the CXU, since each must tolerate suspension of request and response channels. This kind of CXU is apt for a pipelined floating point unit, for example, which might have a multiplier latency of 3 cycles, an adder latency of 5 cycles, and an iterative early out divide unit which has variable latency. The waveform here shows 4 requests and 4 responses and the effects of handshaking and response latency on those requests and responses. CXU-LI compliant CPUs implement CX multiplexing, issuing custom instructions as CXU requests and accepting CXU responses back. The CPU's CXU level will cap which CXUs may be composed with it. For example, an austere single cycle CPU implementing CXU level 0 can only be composed with combinational CXUs, whereas a pipelined in-order CPU might implement level 1 with some fixed latency that all of its CXUs must match. And a complex out-of-order completion CXU might implement level 2 or 3, enabling those more sophisticated CXUs. Level 2 and Level 3 request and response channels, each with valid ready handshaking, map nicely onto AXI4 streams. This is very useful because modern SoC infrastructure provides many AXI4 system interconnects to transport AXI4 stream data all around the chip. Therefore, the basis spec defines a canonical port mapping between the CXU-LI request and response channels and AXI4 request and response streams. This allows a simple, frugal adapter to bridge the CXU logic interface world and the AXI4 streams world. The basis spec logic interface is quite intentionally simple and frugal, but it has some shortcomings. For CPU hardware that doesn't change under composition with CXUs, the design specifies a variety of fixed custom instruction encodings. Also, this repertoire of fixed CX custom instructions can only access the current CX state or the heart's integer registers. You can't access floating point registers or vector registers or memory or the program counter. Also, there's no support for speculative issue and late cancellation of a custom instruction. So for precise exceptions, a CPU must hold off issuing a custom instruction CXU request until it can establish that no prior instruction will raise an exception. While we have focused on the basis specs CXU logic interface, there are several other notable RISC-V extension logic interfaces. Take the Open Hardware Group's CVX-IF interface, for example. Compared with CXU-LI, it's significantly richer, more flexible, more complex, and more expensive to implement. It supports arbitrary custom instructions, shared memory accesses, and speculation. Instead of a single request and response channel, it uses up to 10 channels between the CPU and the extension unit. The first 4, in orange, support decoding of new 16-bit custom instructions and new 32-bit custom instructions. The commit channel, in green, supports cancellation of speculatively issued custom instructions. And the mem channels support custom instructions that access shared memory by proxying the accesses back through the CPU's memory pipeline. All of these additional capabilities and flexibility are powerful, but will be expensive, especially in an FPGA soft processor. Other notable interfaces include ROC from Berkeley, Sky5 from Darmstadt, the V6 vector extension interface from Sci5, and the Pico coprocessor interface. Finally, here's a table comparing various features supported or not supported among different logic interfaces. My apologies if I have some of these checkboxes wrong. In blue are the features of the basis spec CXU-LI that we've already discussed, and in green, the features of the brand new CXU-LI to be specified in our task group. A lot of these features are TBD, to be determined, and soon the task group will start work on this new logic interface, and these features will be decided by the participants. To get this off to a good start, the task group will soon hold a 2 or 3 hour online RISC-V logic interface workshop in early December 2024. We hope to bring together and hear from designers and users of the various RISC-V extension logic interfaces, and together to compare our designs so that we can specify the best logic interface for composable custom extensions. Be sure to subscribe to the task group mailing list for more information. So this is our call to action. The RISC-V ISA is already the preferred ISA for custom computing, and composable custom extensions will further extend this advantage by supporting a new subcategory of custom extensions that can combine the agility of custom extensions with the dependable composability of standard extensions. Our new common framework will make it easier to build such extensions and easier to reuse them. And this will bring a marketplace of reusable extensions IP so that new SoCs can pick from a catalog of accelerated hardware and software solutions, which is perfect for FPGA SoCs. And just imagine never having to re-implement yet another packed SIMD reduced precision 8-bit floating point unit because you can just reuse a perfectly good one that already plugs into your RISC-V core using the industry's standardized extension logic interface. Composable extensions can also extend the useful life of the 32-bit RISC-V opcode space. So in all, this is a really interesting full-stack hardware-software co-design problem with something for everyone: computer architecture, ISA, hardware development, programming models, firmware, OS, libraries, verification, and applications across all the RISC-V market segments. Planning and spec work are ramping up and decisions are being made. So this is the perfect time for you to engage, join RISC-V International, join the task group mailing list, attend its meetings, sign up to work on some of these subproblems, and help us shape the design of composable extensions to best fit your needs. Please join us and make it much easier to build upon each other's good work. Here are some references and resources, including the task group mailing list, its administration home, and its charter, and the Soft CPU SIG's basis spec for this work. Thank you very much for your interest. Okay, let's take some Q&A.